Okay, somebody look at the homework. Okay. Okay, so it's time to get going. Let me just get some microphone. Okay. So today I'm going to write many formulas on the board, but what matters is not the formula, any formula that is on the board, but the commentary behind it, its meaning. So you know that in every test or any exam or any other occasion, the formulas are provided. But the concepts behind the formulas are expressed in words or in ideas that you have to have in your mind in order those formulas to make any sense. So let's start again with most of the formulas actually that I'm going to write are familiar from previous chapter and previous days, previous classes. But the interpretation and putting them together is something that you have to master eventually. So we started, of course, with Coulomb's law for the magnitude of the force between two point-like charges. So the absolute value means that we only work with magnitudes. After that, we defined electric field as force per unit charge. So electric field is something that is almost familiar because you're familiar with forces. This entire first semester we dealt with forces. So electric field is a force that acts on unit charge. That's it. Electric field at certain spot, at certain position, is a force that a test charge placed at that position would experience. After that, we said that the electric field that is generated by a single point-like charge is this. Again, the charge has to be in magnitude, but because the electric field here, yes.
Is the force in the electric field equation, the first one, the same as the force above? Those are the same, right?
Is the force here exactly the same right here? The answer is yes. Okay. But notice that here the force is a vector, while here it is in magnitude. So this means that this first formula doesn't give you everything about the force. It just gives you the magnitude of the force and the direction we describe with words: attractive, repulsive force. Okay, let's see what else. So we introduced electric field this way. Notice that everywhere we have this constant of proportionality K, which describes electrical properties of empty space, of vacuum. Alternative description of the constant K would be 1/4 pi epsilon naught, where epsilon naught is electric permittivity of vacuum. Or air practically has exactly the same. Practically exactly the same electric permittivity. Okay, so now we have electric fields. We used Gauss's law to find the electric field between two very large plates, one of them charged positively, the other one charged negatively, the same magnitude of charge on them. And we calculated that electric field between the plates of this so-called parallel plate capacitor is, what is it? Surface charge density in magnitude on one of the plates divided by electric permittivity. A vacuum if the space between the plates is vacuum or air. Here, the surface charge density sigma is just amount of charge again in magnitude per unit area. So this came from Gauss's law, and it is useful because we'll see why. Well, the next part of the story was dealing with energy, and the simplest result was, well, it was not a result, we just made a hand-waving argument about that. The electric potential energy of a system of 2 point-like charges separated by distance r is just given with the product of the charges divided by the distance between them, and the same constant of proportionality is needed. Unlike previous formulas, well, even here you probably have to put absolute value sign, but in the electric potential energy formula, the charges Q1 and Q2 enter together with their algebraic sign, positive or negative. Using the concept of electric potential energy, we did something similar to what was needed to in introduction of electric field, right? So electric field is a force per unit charge. Electric potential, or we call it voltage, is energy, electric potential energy per unit charge. Just like electric field was force per unit charge, exactly the same story here. And again, the voltage created by a single source, single point-like charge, is easily written, and I'll write it here. The voltage created by a single charge at a point that is at a distance r from that charge is given with the value of the charge divided by the distance times the same constant of proportionality. Again, now we have to take Q together with its algebraic sign. So the last three formulas, this one, and this one, assume that the voltage, the electric potential at infinity becomes zero. Infinitely far away from any charges, the electric potential becomes zero. Or alternatively, the electric potential of the planet of Earth is also zero, just like we talked before. So those are the formulas that, last time we also introduced the concept of capacitance, right? So we started talking about two parallel plates, charged, one of them positively with charge positive Q, the other one with negative charge Q. Area of the plates A, and we said, okay, here is a diagram. One plate, another plate, this one with positive charge, this one with negative charge, magnitude of the charge Q. Let's say that the separation between the plates is D, and let's say that the surface area of each plate is A. Well, Gauss's law allowed us to calculate the electric field between the plates, and it is everywhere the same. So closer to this plate, farther from that plate, here, 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 the electric field always has exactly the same magnitude and also exactly the same direction. Electric field lines are like this. Now, let's call the voltage difference, the potential difference between this and this plate, potential difference V. So sometimes we use the notation delta V, the difference between the potential at plate left minus the plate right. But very often, and in the formulas in the textbook, the delta sign is skipped. We just keep in mind that always when we calculate some voltage, we calculate actually a voltage difference between 2 points. One of those 2 points may be at infinity or in the ground, but it is always a difference of voltages. So last time we said, well, if the 2 plates have certain amount of charge Q in magnitude, the voltage is going to be voltage V. After that, you may decide to double the charge. You're going to discover that the voltage difference also doubles. In other words, you experimentally notice that the amount of charge is proportional to the voltage difference between the 2 plates. And the coefficient of proportionality you call capacitance. Capacitance is measured in coulombs per volt, that we call coulomb per volt, we call farad. And we said farad is a very large capacitance. You need a capacitor, quite bulky capacitor to get 1 farad capacitance. Now, talking about capacitors, we need a formula that allows us to connect the electric field at certain place with the voltage around that place or at that place. So those are 2 separate descriptions of electric phenomena. You can describe electric phenomena in terms of electric field, or alternatively, you can describe electric phenomena in terms of voltages. And we said, well, voltage description seems to be simpler because voltage is a scalar number, positive, negative, but a number, while electric field is a vector. And the rules for working with vectors are more complicated in general. So the dictionary formula that connects the 2 descriptions, electric fields and vectors, looks like this. The electric field at some place is equal to the change of voltage per unit step size, delta x. There is a minus sign, which for us is not going to be useful, but it's a good style to keep it. Just it's a matter of convenience. So what does this formula tell you? It tells you that, let's say that you want to calculate the electric field at this spot right here on the board. What you have to do is take the voltage at a neighboring point, take the voltage at another neighboring points. So the neighboring points are separated by a distance delta x. The voltage difference between those 2 neighboring points is going to be some number delta V. And the electric field is going to be the ratio of the voltage difference to the length of the distance between the points, with a few additional descriptions. The step size delta x has to be infinitesimally small. And on top of that, the step delta x has to be along the direction of electric field lines in order this formula to work properly. So it's a complicated kind of description, but it tells you that electric field is the rate of change of voltage. You have change of voltage, you must have some electric field. That's it. Well, look, now using this dictionary formula, by the way, this dictionary formula is quite important. In order not to deal with those minus plus signs, I'll put absolute value. And the direction of the electric field we have to figure out using diagrams, as we are going to see in the examples that we're going to solve today. Okay, knowing all of this, we can find the capacitance of a capacitor, parallel plate capacitor, the capacitor that is drawn on the board. How to do it? Well, we said that we're skipping the sign, the delta symbol. In other words, this formula, this dictionary formula, can be written as voltage divided by distance, in a sense. Well, this is even worse way to write it, but this is notations that are simpler. So I kind of don't want to write it, but I need simpler notations. And look now what we're going to do. Consider this parallel plate capacitor, distance between the plates d, area of the plates a, charge on the plates q, and voltage difference v. You know what is the electric field between the plates. The electric field between the plates is this. I can write this electric field magnitude E as magnitude of Q divided by area and divided by epsilon naught. And now I can use the dictionary formula to write, instead of electric field between the plates, to write something about the voltage difference between the two plates. So to do that, I'm going to take a step size as large as the distance between the plates. In other words, this step size x, I'm going to make it as large as it could be. And it is perfectly valid way to do it because the step size d also is going to be along the electric field lines as it should be. So you can take even non-infinitesimally large step. So substitute the electric field with dictionary formula, and you're going to get that voltage divided by the distance between the plates. Voltage is the voltage difference between this and this point, between this plate and the other plate. In magnitude, that electric field or this voltage per distance is equal to charge divided by area and epsilon naught. And finally, take this from denominator to the other side denominator, and you're going to get an expression that looks like this. Charge on the plates is equal to area of the plates times electric permittivity of vacuum divided by the distance between the plates and multiplied by the voltage between the plates. So all of this was reasoning that is perfectly fine if you don't follow it. But the result is interesting because the result reminds you something. Look, charge is proportional to voltage, coefficient of proportionality C. Charge proportional to voltage, coefficient of proportionality, this oval. So when you compare the definition for capacitance, this expression, and the result that we got, the conclusion should be that the capacitance of a parallel plate capacitor with air between the plates is given with area of the plates times electric permittivity of air divided by the distance between the plates, D. Capacitance of a parallel plate capacitor. So again, I probably have to clean a little bit of real estate here in order to accommodate the formulas that follow. But the formulas that are important, I'll try to keep. So probably this bad writing can be removed, and this derivation can be removed, and the result is right here for the capacitance, so I can remove this also. Well, let me copy what I just area epsilon naught d distance d. Okay, let's see questions and remarks because I see that you're kind of bored and don't see the point of all of this. Anybody? At least a question about my handwriting. So my letter G looks like, I don't know, doesn't look like letter G. Yes.
So I was reading the book, and I know another equation that I found for capacitance was also capacitance equals the constant of proportionality times epsilon naught times area over T. Is that the same thing?
It is good actually that at least one person read the chapter. So the question is, well, what I have written is similar to what your colleague read. What is missing is the constant of proportionality, right? I can write it, but give me a minute and I'll write that constant of proportionality in a minute. Because, look, this formula tells you that you have larger capacitance if the area of the plates is large and if the distance between the plates is small. You're going to see in a minute that capacitors, among the other things, can be used as energy storage devices. And if you go to Best Buy or to Amazon, you can buy actually devices that store energy indefinitely, long time, infinite lifetime, that are practically a capacitor. The larger the capacitor, the more energy you can store, as you're going to see in a minute. And the question is how to store more energy. So let's first figure out how much energy is stored in a capacitor. And after that, we're going to think about how to increase that energy storage. So look, to figure out the amount of energy stored in a capacitor, remember that we calculated the work that is done when a charge moves from a point with voltage V to a point with voltage V prime. And that work roughly is going to be equal to the product of the charge times the voltage difference between the 2 points that this charge moves. It is practically this formula, but written as, instead of energy, I say work is equal to charge times voltage difference between the 2 plates, between the 2 points where the charge Q moves. So using this formula for work, you can figure out how much work is needed you to charge the capacitor to certain value. So start with a capacitor that is not charged at all. And first, you take one electron right here from this plate and you move it to the other plate. You can do it practically for free. Just grab the electron, move it there. Practically no effort needed, no work needed to do that. Now, when you take the second electron, you're going to have to do some work now. Because look, once you removed an electron from this plate became positively charged. Once you placed the electron on the other plate, that plate became negatively charged. And now, if you want to move the second electron, that second electron is attracted by the positive plate, the positive plate doesn't want to lose it. And that electron is going to be repelled by the negative plate. So you have to apply some force. You have to do some work in order to bring that second electron to its place. Moving the third electron is going to be even harder. And of course, as you're moving charges, the voltage difference between the plates also increases. So you can say that the amount of work that you do to move charge Q between plates with voltage difference V is this expression. But your process of charging, you start with voltage difference 0 when the plates are not charged at all, and you reach some final voltage difference V. So if you want to use this formula, you don't know what kind of voltage difference between the plates you have to use. You started from 0, you ended with certain value V, 10 volts or whatever. And the answer you can demonstrate using a little bit of calculus, that you have to take the average between 0 voltage and the final voltage that you reach after you move multiple electrons. And therefore, the energy stored in the capacitor, I'll write it like this. Energy stored in the capacitor, which is also the work that you do in order to charge that capacitor, is Q times V, but V average. And average V is 1/2, because you start the average between 0 voltage and the final voltage, you get the average is 1/2 of the final voltage. So this is the energy stored in the capacitor, but this expression is not useful for practical purposes, because you can measure the voltage difference with a voltmeter, but the amount of charge that is stored on a plate is harder to measure. So you have to trade this, you have to replace this charge Q with something equal, and the convenient replacement would be from this expression. So substitute Q with its equal. And you're going to get that the energy stored in the capacitor, which is also the work that you did to charge it, is going to be equal to 1/2. And in state of Q, I'm going to have capacitance. And in state of voltage, I have voltage squared. One voltage from here and another power from here gives you voltage squared. This is a more standard way to write the amount of energy stored in the capacitor. Right? This is, I'll remove the previous version because this one is more convenient. Capacitance is something that, well, you can measure. Many multimeters have, you can change the measuring to go to a capacitance, or you can just read it from, here is one capacitor, you can read the capacitance of this capacitor, it is typed here. This one is a relatively small capacitor in size, but large enough so you to see it. Yeah.
Can you also replace that capacitor value with a charge value to also find the energy of the capacitor?
Well, I had it actually, right? I had that energy was 1/2 charge times, what was it? Okay. I had that, but again, the argument was more convenient expression of the same thing is to substitute Q with capacitance times voltage, and you get that. So look, now if you want to store energy in a capacitor, you can increase the capacitance, or even better, you can increase the voltage between the plates. So here is, here's a parallel plate capacitor, two metal plates. Here are two metal plates. They're not separated by air at this point, but you got the idea. I want large capacitance. Large capacitance can be achieved by increasing the area. And here, this is huge area. It is just rolled, not to occupy too much space, but area is large. And the distance between the plates is the thickness of one piece of paper or something. So if I have only air between those plates, the capacitance of this capacitor would be expressed as area times electric permittivity of air divided by distance between the plates. Now, okay, this capacitor has probably capacitance of the order of maybe a fraction of a farad. But if I want to store even more energy, what I can do is, according to the last formula, I can increase the voltage between the plates. So I can put, let's say, voltage of 50 volts, increase it to 100. This is going to increase substantially the amount of energy stored in this capacitor. But look what happens when the voltage between the plates goes too high. Look what happens in that case. So here is one plate, here is the other plate. When the voltage reaches certain value, electrons are emitted from the negative into the positive. Those electrons ionize the air molecules. The ions get accelerated and you have a spark, and the charge is lost. The spark also can destroy the capacitor by destroying either the plates or. So if you want to increase the amount of energy stored, you have to prevent the sparking. And you prevent the sparking by placing material between the plates that is a better dielectric, that doesn't allow a current, a spark, to propagate from one plate to another. So look what happens. You place some material like that piece of paper-like material here between the plates. In general, the molecules of dielectric materials are either polar with plus and minus at two ends of the molecule, or they become polarized from the field between the plates. So here are some molecules, plus, minus, polarized polar molecules like this, oriented this way. And those oriented molecules, they are oriented in the field of the capacitor, there of the field between the plates. Those oriented polar molecules generate their own field, electric field, that points in opposite direction. The net field, the field between the plates and the field generated by the molecules of the dielectric partially cancel out. The net electric field is reduced by a factor. So if the electric field, when you have air between the plates, is E naught, and the electric field, when you place the dielectric material, is E, the coefficient of proportionality between the coefficient of proportionality E naught is equal to kappa times the electric field, the net electric field when you have a dielectric. This coefficient of proportionality kappa, or K, if you want in your textbook, curly K, is called dielectric constant. It tells you the factor by which the electric field is reduced due to the presence of dielectric material. Well, from here, you can also see that the voltage between the plates also drops proportionally to kappa, right? The voltage when you have air between the plates is V naught. The voltage after you place the dielectric material becomes V. The coefficient of proportionality again is kappa. The same dielectric constant. In other words, when you repeat the same procedure like we used to calculate the capacitance of a parallel plate capacitor, but now take into account that the electric field is reduced by a factor of kappa, you're going to get that the capacitance of the capacitor is multiplied by a factor equal to the dielectric constant kappa. So I will remove those definitions here, and just will leave this factor of kappa in the capacitance of the capacitor. The dielectric constant of air or vacuum is 1. They don't reduce voltage or electric field. And the dielectric constant of good dielectrics could be of the order of 1,000. So this is why between the plates of a parallel plate capacitor like this one, you have this dielectric paper-like material. This increases the capacitance of that capacitor. And again, this capacitor, you fold it like this, put it in a aluminum box, and here it is a large capacitor. This one is large capacitor with capacitance. Well, I have to figure out. But the capacitance of this capacitor could be of the order of a fraction of a farad, let's say 100 millifarads, 0.1 farad or something like this. For practical applications in old TV sets or radio, you have variable capacitor. Look, the plates of the capacitor are movable. Only the area that overlaps counts. And you change the capacitance of this capacitor just by turning the knob. Okay, too much talking. Let's see remarks, questions, issues, comments.
The dielectric, is that a constant?
The dielectric constant is a constant for given material. So the dielectric constants for different materials are tabulated. And I think that there is a table of dielectric constants in the chapter, in the textbook. So you need materials with large dielectric constant for a good capacitor. And usually, well, they use everything from some ceramic material, like for in this small capacitor, ceramic material, something. Yes.
So if I understand this right, you want the dielectric material in between because it just allows it to basically increase everything without the spark.
Exactly. You increase the voltage difference before the spark starts. So if it is only empty space, air or vacuum, sparking starts at about 10,000 volts for every centimeter of separation. 10 to 30,000 volts depending upon humidity and temperature. But once you place here dielectric material, the sparking is not going to start until you reach, let's say, 100 kilovolts per centimeter of separation. Yeah, as simple as that. But again, keep in mind that if you have dielectric material between the plates and you exceed the voltage difference, so a spark starts, that spark is going to damage the dielectric. It's going to burn it, practically. And you lose the capacitor. Because instead of dielectric, you're going to have some semiconducting stuff between it, and the capacitor is not able to. Now, one last important result at the end of this section. This formula gives you the energy stored in a charged capacitor. But it kind of implies that that energy is stored in the plates of the capacitor because it includes the voltage between the plates. So you can interpret this formula, and especially this one, as if the energy is stored on those metal plates. But now, do the following thing. Let's say in this formula, substitute the capacitance with its equal. Let's keep it. Let's say the capacitor is filled with air, so the dielectric constant is 1. Just to have it as a simple expression. Also, substitute the voltage between the plates with the dictionary formula expression which said that voltage divided by distance gives you electric field. In other words, voltage is distance between the plates times electric field. So substitute this for V and look what you're going to get. You're going to get that the energy stored is equal to 1/2. So in state of capacitance, I have area, epsilon naught, distance. And in state of V squared, I'm going to have distance squared, electric field squared. So some more complicated expression, but look, I can cancel 1 power of distance. Also, area multiplied by distance, so area of this plate multiplied by distance gives me the volume between the plates. So I'm going to have energy is 1/2 electric permittivity of air or vacuum times volume times electric field squared. And look, this means that energy per unit volume is equal to 1/2 electric permittivity of air or vacuum times the squared. So this is important result that gives you completely different interpretation about the energy location, where the energy is stored. The previous formula implied that the energy is stored on the plates of the capacitor. This formula doesn't say anything about plates of capacitor because electric field exists only in the space between the plates. This formula tells you that the energy is stored in the space between the plates rather than on the plates itself.
Where did you get volume? Sorry.
Area times distance between the plates. Area times distance gives you the volume. This is. But the formula is more universal. It tells you that if the electric field created by this Van der Graaf here is, let's say, 10 newtons per coulomb, the energy density of this place is going to be 1/2 times epsilon naught times 10 squared joules per cubic meter. At different spots where the electric field is different, you get alternative energy density of different spots and so on. So the interpretation of this formula is that energy is stored in space where electric field leaves, rather than on the plates where charges leave. So knowing this, in the remaining minute and a half, let's think about problem number. Well, problem 16 is slightly different from, it is from the old material.
Number 22.
Number 20, let's see what is number 20. Oh yes, number 20 is pretty much what we talk here in this. So here is problem number 20. So again, you have some place, and actually, in problem number 20, the diagram that you're going to see in a minute looks like this. You have uniform electric field. How do you create uniform electric field? With this parallel plate capacitor. Just the plates now are positive here, negative plate here. So you have given uniform electric field, and you are given some points between the plates of the capacitor, you are asked to figure out the voltage difference. Look, part A is easy. Those are electric field lines. The equipotential surfaces are perpendicular to the electric field lines. Therefore, point A and point B live on the same equipotential surface. They have exactly the same potential. They have exactly the same voltage. Therefore, voltage difference between A and B is 0. Just by looking at the diagram. To find the voltage difference between point C and B, you use the dictionary formula. Here's the dictionary formula. If you take a step size equal to the distance, in my case, 8 centimeters, that step size is long, but it is along the electric field lines. So in that direction, you can make a step of any size. And therefore, you're going to have that the voltage difference, delta V, between those two steps is going to be the distance of 8 centimeters in meters. So it is distance D times the value of the electric field. In other words, it is 0.08 meters multiplied by whatever electric field they give you. Now, careful with algebraic signs. We skipped algebraic signs, but we can easily restore the algebraic signs because look, you have electric field in this direction indicates that positive charges are located here and negative charges may be located here. Therefore, point C that is closer to the positive charges must have higher potential, higher voltage than point B, which is farther away from positive charges and closer to the negative charges. Therefore, the voltage at C is higher than the voltage at B, and therefore the difference between C and B is going to be a positive number. In a similar manner, you make the argument for part C. Just keep in mind that the voltage at point B is the same as the voltage at point A. So basically, this difference is the same as the previous one, but with opposite algebraic sign. So think about it, and if necessary, we're going to discuss again next time.
You have some online questions.
Yes.
First one being the dielectric constant will be given on the exam.
The dielectric constant for air or vacuum is 1. And if it is some other material, of course, it has to be given, and it is different number for different materials. It is a number larger than 1.
Okay. And then it said on the syllabus that the first exam was January 28th. Does that change?
Yeah, we have to change the date of the first midterm exam. If anybody insists, I can put together a midterm exam for January 28th, but for the moment, relax. I have to put together a practice test first, and after that we have to talk, and after that we can do the midterm.
And then the last question was if there's still the people that won't be able to come to Pocatello for the exam. Have you talked to Dr.
Some people that cannot travel, we're going to accommodate them. Those people just have to be patient and be ready, and we're going to arrange some way for those people to do the exams.
Okay, I think that's it.
Okay, so in that case, see you guys on Friday.